We're very pleased to have Valentino Tosatti from Northwestern who will give an introduction to case theory.
Okay, thanks a lot for the invitation also. It's good. So, well, I believe case stability was defined at some point in Ian's talk, but I'm going to define it again, but not at the very beginning. Instead, I want to kind of have a seamless continuation of Claude's talk. So very briefly. So to start, we'll have a compact Kähler manifold X. Omega is the Kähler form, and I will do the deadly sin that Claude was referring to earlier of using omega to denote the Kähler metric as well. So omega and G for me are interchangeable. That's when the complex structure is understood to be fixed. And throughout this talk, it will always be actually a projective manifold. So I will assume that there is a holomorphic line bundle L over X such that the cohomology class of the Kähler metric is equal to the first chunk class of L. I will mostly ignore factors of 2 pi, also in definitions of first chunk classes. So there will be no 2 pi in my talk. But usually you might want to have a 2 pi in here somewhere. So in particular, this says that the line bundle L admits a metric that exists H, a Hermitian metric on L, on the fibers of L, with curvature essentially omega, positive. The curvature is, again, up to a factor of I and 2 pi is omega. So by the Kodaira embedding theorem, L is ample. So by Kodaira, we know that the sections of a sufficiently high power of L will give me projective embeddings. From X. This should be for all K sufficiently large. So I can regard X as a smooth algebraic variety. But the point is that there are several different ways of embedding into higher and higher projective spaces. And each embedding is not canonical. It depends on a choice of a basis, for example. So there are many different ways of embedding X in projective space in this way. And so this is the basic setup. And I'm going to, again, look at the Ricci curvature. I guess Claude talked about it, of G, which is going to be a tensor. I'm not really going to use it. This is just be the only time I'm going to use it. In local holomorphic coordinates, this would be dz bar j of log determinant of the metric in local holomorphic coordinates. So what's going to be important is, first of all, I can package it into a Ricci form. Ricci G or Ricci omega, which will be like this, the same way as you obtain the Kähler form omega from the metric G. And this Ricci form is a closed real 1-1 form with cohomology class. Again, really it's 2 pi times the first chunk class of L, of the manifold. So of X. Well, with your permission, I'm going to drop the 2 pi. It's really there, but otherwise it has to be throughout the whole talk, where the first chunk class of X is just the same as the first chunk class of the, well, by definition is the first chunk class of the tangent bundle of X, and that's the first chunk class of the determinant, which is the anti-canonical bundle of X. Yes. Minus Kx. I'll use this kind of algebraic notation for line bundles. Okay, and then So the Ricci curvature can be packaged into this form, which has at least this intrinsic global property of being always cohomologous to the function class. Note, this does not depend on omega, of course. When you pick different metrics, the cohomology class you get is always the same. There's a 2 pi here. But yes. And I mean, I think people usually put the 2 pi here in the denominator. Also, there is the scalar curvature. I guess Claude mentioned this too. G, which is Gij bar Rij bar. S of G or S of omega. Again, my abuse of notation. And the point is that this is a smooth function, real valued smooth function, and the integral of the scalar curvature. So if I integrate using the wedge product of the Kähler form n times, so by kind of simple linear algebra exercise of what doing the trace means, this becomes n times the integral of the Ricci form, wedge omega to the n minus 1, if you want to prove this identity. And this is purely cohomological. This is n times, so the Ricci form is in minus kx, and omega is in the function class of L. So it becomes this intersection number here, minus kx dot L to the n minus 1. If you don't like intersection numbers, just view this as the integral of the first form of any metric here, any metric here. Yes. Okay, so in particular, if I denote by underline S, the average of the scalar curvature, so this is the average scalar curvature, which I'll use all the time in this talk. This is just the integral of the scalar curvature divided by the integral of the function 1, so the volume. So this is purely cohomological. It's again n minus kx dot ln minus 1 over ln. Again, if you're a purist, the omega to the n is not quite the Riemannian volume form of the Riemannian metric associated to G, because it differs from it by a factor of n factorial, which of course I don't care about. And anyway, in this formula, the n factorial is cancelled, so this is correct regardless. Okay, so the problem that main problem that we were going to be interested in, which was the one that Claude discussed quite at length, is when can we find omega tilde Kähler metric on X in the function class of L, so we should say with, so cohomologous to omega, and with constant scalar curvature. So the scalar curvature equal to its average. So this is the equation of constant scalar curvature Kähler, usually abbreviated by CSCK. So I will use this shorthand throughout the talk, right? Of course, if the scalar curvature is constant, the only constant it can be is its average. Yes, so that's why it's here. And the average is purely topological, you can say. It depends only on this intersection number, depends only on the class. So you can think of this as being given to you, and you want to find a metric with the scalar curvature equal to this constant. Yes, so this one, as Claude mentioned, is a generalization of the uniformization theorem, I mean, as a question, as a problem. And it is not the most general question of this type that you can ask. In fact, you might have heard of extremal Kähler metrics. That's a more general class of Kähler metrics that satisfy a more general equation, which have very similar properties. I will ignore them because they just introduce useless technicalities for this talk. But just keep in mind that most of this story can be extended to extremal metrics with some technical minor changes. But I won't define them, so there's no need. So the examples are Well, this equation says the scalar curvature is constant, but this one is the contraction of an even better equation. The Ricci curvature is constant. Which one? No, not yet. Not yet. Yes. I guess it would be on the next slide, but not yet. So no, minus kx could have any positivity or non-positivity for now. And so the examples are Kähler-Einstein metrics. So here, I believe Claude mentioned these two. These are metrics like this, using my notation. The Ricci form is a constant multiple of the Kähler form, or if you want, Rij bar is lambda Gij bar, the Einstein cosmological equation, vacuum equation. So first you notice that by scaling, if you rescale the metric omega tilde by a constant positive factor, like twice the metric, this one scales twice. This one doesn't scale. It's dd bar log, two derivatives. So by scaling, you can always assume that, in fact, lambda is just -1, 0, or 1. Otherwise, you just rescale the metric. Yep. So by taking the cohomology class, so of course, this one implies constant scalar curvature. Right? This is lambda times the trace of this, which is the complex dimension. And also, if you take the cohomology class of this equality of forms, you conclude that the first Chern class of, what did they say, minus kx is equal to lambda times the cohomology class of omega tilde. So if lambda is 0, this equation just says that the first Chern class is 0, which is the condition of Calabial. X is called Calabial. Non-standard definition, possibly. So the wider definition of Calabial. This is not. There is no standard notion of Calabial. It's just the one I call. And then, but if lambda is non-zero, then this forces this class to be ample or anti-ample. So if lambda is positive, this implies that minus kx is ample, positive. If lambda is negative, this implies kx is ample. And furthermore, it implies that the cohomology class is actually equal to plus or minus the canonical class. Right? So in these two cases, the cohomology class of the metric is fixed. And then simple exercise is that if you are in any of these three cases, so if you forget about Kähler-Einstein, let's say if you have either Calabial or kx ample or anti-ample, and if you have a solution of this equation, constant scalar curvature, in the correct class, then it implies Einstein. So this actually implies the one above in these three cases here. So in fact, the so-called Kähler-Einstein case, when either the canonical bundle is, this is equivalent to saying that kx is holomorphically torsion in peak. So if kx is torsion, then constant scalar curvature, lambda must be 0 by the calculation. Constant scalar curvature is the same as Ricci flat. And if the canonical bundle is ample, and you are in the correct class, in the canonical class, then again, constant scalar curvature is equivalent to Kähler-Einstein, and same for the other case. Right? Okay, so these ones are called Fano manifolds, in case you never heard of it, but probably you did. Fano varieties, so these are smooth Fano manifolds. They're the ones with, shoot, I picked the wrong line. I meant this one. The anti-canonical bundle is ample. This one is a special case of general type, so these are of general type. Okay, so the point of this is just to say the constant scalar curvature problem is a generalization of this Kähler-Einstein problem, and it's equivalent to it if the cohomological conditions are satisfied, and otherwise, this is harder. So, but this is already, I mean, the analogous problem for Kähler-Einstein is already pretty hard, extremely hard. So, I think maybe Claude mentioned it. Let me just say in a few words. So this problem here is completely solved in cases 2 and 3. Sorry, 1 and 2. 1 and 3. And recently, also in the middle case, that's going to be what I want to talk about. So let me just mention first these two. So if lambda is 0, so if the first-chain class, say of kx, is either 0 or ample, so maybe I should remove first-chain class. If kx is either torsion or ample, then there always exist Keller-Einstein and constant scalar curvature metrics. Then C as Ck, as I said, the same as Ke in this case, always exist. And they're unique in their class. So let me attribute this. This is a famous theorem, Calabial Theorem. So Yau solution with Calabi conjecture in the case that covers this, and also independently Oban for the case of Kx ample. This is yes. In this case, L is plus or minus Kx. So meaning here, okay. Here L is anything you want. Ample. Here L is minus Kx, here L is Kx. So here, yes, I'm stating in that way. So in other words, in words precisely, if Kx is ample, then there exists a unique Keller-Einstein metric with lambda is minus 1, Ricci is minus omega. And if lambda is 0, then in each Keller class, there exists a unique Ricci-flat Keller metric. So this says you always have existence in those two cases, and you have uniqueness in their polarization class. Okay, so the case when minus Kx is ample, so the Fano case, turned out to be much harder. This was already a major result, so the proof is not simple at all. This case was even harder. So if minus Kx is ample, there are obstructions to the existence of CSC K, in this case again Keller-Einstein. These are the same. So let me describe historically not the first, I think probably the second obstruction that came up, but it's the one that is most relevant to case stability. So the other one is relevant too, but that's a Matsushima's obstruction, but I don't have time to mention it. So the obstruction, or one obstruction, in fact, this would be the general obstruction for this general case, is the Futaki invariant. So pick any, say, X, L. In fact, you don't even need a line bundle here. Just a Keller class is enough. But let's say as before, omega Keller metric in the first class of L. Any Keller metric. So usually it won't have constant scalar curvature. So this difference won't be 0. But this has average 0 by construction. And so by Hodge theory, it can be written as the Laplacian of a function. So hence there exists a smooth function f such that this the Laplacian of f. This is just the trace of dd bar of f, or the trace of the complex Hessian. J bar. Or if in other words you take dd bar f and then take the trace using the metric. Okay, so this is the first ingredient. And the second ingredient that I need is a holomorphic vector field. So let V be any global holomorphic vector field, so a global section of the holomorphic tangent bundle. I'm dropping the 1, 0. It's always understood to be the holomorphic tangent bundle. Then Futaki defined the following object. I'm going to put G for now, Futaki G of V. You just take this vector field V, apply to the function f. A vector field can surely eat a function, differentiate a function. You get another function, and you integrate it with respect to the volume form of the given metric. So you get a complex number. So in other words, you get a linear map from H0 of kx into C. Yes? And as defined, it depends on the metric G. For once, the function that you get here depends on G. And second, there's also the volume form. So it depends on G in those two ways. But actually, it's independent of G. So the theorem of Futaki, and I believe also Calabi later. So Futaki first in a slightly more restricted situation, and then Calabi is around 82, 81, 82. This Futaki invariant is independent of G in its class of G in a fixed C1 of L. So if you want, it depends only on the cohomology class of omega, what they call it. Or if you want, it depends only on the polarization L. So I'm going to drop the G or put it as a class. This is not trivial. You can try to prove it yourself. And it's not that easy. It's a little bit easier in the Keller-Einstein Fano case. So in the Fano case, actually you can integrate this twice. It's going to be Ricci omega minus omega. It's actually dd bar f, and the proof simplifies quite a bit. That was Futaki's original paper. Okay, so what's the point? The point is that if you have a Keller-Einstein metric in the class, so if there exists omega Keller-Einstein, surely I can pick f to be the 0 function, because this vanishes. And therefore, this Futaki invariant just gives me 0. And since it's independent of the metric, that means that the Futaki invariant vanishes in the class. So conclusion, if this Futaki invariant, let's say, I keep changing my notations, this means, maybe I can call it L, say, of the class of the line bundle L. If Futaki is not identically 0 as a map from holomorphic vector fields to C, then there is no CSCK metric in the first-gen class of L. And so it's a good result. And the point is that this Futaki invariant can actually be computed. If your manifold is explicit, the vector field is explicit, well, this guy's not explicit. Even if the metric, if you pick an explicit metric, then you need to solve the solution of the inverse Laplace operator. So this won't be explicit. But you can compute it via localization formulas. So it usually is quite computable, although it's not a trivial task to compute it. So the simplest example is when x is the blow up of CP2 at one point, and take L to be minus kx. Then probably this was the calculation in Futaki's paper. I can't remember. This is Futaki does not vanish. Does not vanish identically, which means there is no constant scalar curvature, but in this case, as I told you, must be Keller-Einstein. So there is no Keller-Einstein metric on X. So this was the, this can also be obstructed by Matsushima's earlier obstruction though. So probably that's not the one that you can find in Futaki's paper, because he wanted to find a new example which wasn't obstructed by Matsushima, but is obstructed by his new invariant. But this is easier. So it's also obstructed by Matsushima. Matsushima just says, in this case for Keller-Einstein, yeah, the automorphism group must be reductive in the Keller-Einstein case. So here it's not reductive, so that also obstructs. Okay, so there are abstractions, and before we get to that, the point is that it emerged that the existence is equivalent, or a conjecture emerged that existence is equivalent to if and only if some notion of stability, which, as you know, it's turned out to be K-stability. But before we get to that, let me mention a little bit about energy functions and what the analytic motivation was for having stability enter the picture. I think Claude mentioned that because of this result, a lot of people believe that this was kind of the only abstraction in a sense. Namely, for example, if you had no non-zero holomorphic vector fields, then this abstraction is void. And they thought that then say, all Fano manifolds with no holomorphic vector field had to have Kähler-Einstein metrics. And this was disproved by Tian in 1997. So it is not the only abstraction apart from this Matsushima. So before we get there, a few things about energy functionals, just the simplest ones, because these are going to be infinite dimensional analogs of notions in GIT, the log norm functional that I think at some point featured in Ian's talk. So the first one is much easier. I'm just going to mention two. The Calabi energy. So from now on, let's see, maybe let's denote it this way, HL to be the space of all Kähler metrics on X with Furchen class L. So these are omega. So all possible Kähler metrics in the Furchen class of L. As I think Claude did mention, maybe I should call them tilde. If you are given one such guy omega, so given omega, then any other one must be of the form omega plus I dd bar of a function phi. This is the imaginary unit, where phi is a smooth function, real valued, unique up to addition of a constant. This is also Hodge theory, the Kodaira's dd bar lemma. So in a sense, this HL, the space of all Kähler metrics in a fixed polarization class, can be identified with a space of smooth functions modulo constants. So if you want, it's the same as the space of all phi, a subset of the space of all smooth functions. This subset, shoot. So all smooth functions such that this is strictly positive. This means it's a Kähler metric, modulo constants, addition of constants. So this is an open, or maybe without modding out constants, let's say, this is an open convex set, open convex subset of the space of smooth function. It contains the origin. The function 0 is definitely in there. So convex, so it has really no topology. It's just a contractible space, but it's infinite dimensional. And in fact, it has a natural L2 metric. L2 Riemannian metric, namely, I won't really need it, but just so you know. Namely, let's forget about the constants. So let me look at this one above. The constants are just normalize the potentials to have, say, integral 0 that takes care of the constants. So if you look at the tangent space of this guy, it's just going to be smooth functions because it's an open set. So a tangent vector to this guy above is just a smooth function, real valued. And you can define the inner product, or say the norm, the inner product, say u, v. These are smooth functions at a point. This is the tangent vectors to h at a point phi. And you define this to be like this, where omega phi is omega plus d bar phi. So the obvious L2 metric, the only thing is the volume form is the volume form of the point which these vectors are tangent at. And this one is formally infinite dimensional Riemannian metric. It has a Levi-Civita connection. And in fact, it makes this space into a symmetric space, negatively curved, formally negatively curved symmetric space. That will not enter the picture here, although if you want to go to this more deeply, it's one of the crucial points in this analogy between finite and infinite dimensional pictures. So, no, Calabial energy, sorry. The Calabial energy is functional Cal, say from this HL to R. It's just maps omega to the integral over x of scalar curvature minus the average squared. So it's just the L2 norm squared of the scalar curvature minus the average. Looks like a trivial functional. Well, of course, it's non-negative, and it's 0 precisely as constant scalar curvature metrics. And then Calabi computed its first variation and second variation, in fact, on this space. And the critical points, in general, are more than just constant scalar curvature, which are obviously critical points. They are the so-called extreme Keller metrics. So they are the solutions of the Euler-Lagrange equation. In any case, this is the simplest type of energy functional. And then the next one is more interesting. So of course, you can view this problem of finding CSCK as a minimization problem for this functional, but that's totally a trivial reformulation. It doesn't give you anything new. Yes? There's a much more interesting functional, the Mabuchi energy. So this is around 87. So you do the following. So this one depends on the metric. So given reference metric omega in the first class of L, define this guy. So defined as following. So if you have a guy here, now I'm going to call it omega tilde, which is omega plus dd bar phi. So then you pick any smooth path connecting, or maybe I should say in HL. Actually, I'm being sloppy again. A path in the space above without quotienting. Any smooth path connecting phi and 0. For example, you can take phi t times phi. That's the simplest path, since it's convex, and path phi t. T is between 0 and 1. And then you have omega t, omega plus dd bar phi t. For example, this t times phi. These are Kähler metrics by assumption. And then you define Mabuchi omega applied to omega tilde. So you want to integrate again scalar curvature minus the average. This one doesn't depend on t. So here you want to put the first variation of the path, phi t dot d by dt of phi t. So then you integrate over the manifold, omega t, and then you integrate over the path in dt. And then you put a minus sign for reasons that you will see later. So this functional here is well defined, independent of the choice of path. And for example, you can get a pretty explicit formula by picking this pretty explicit path, but it's not important for us now. The point is, by construction, the critical points are exactly constant scalar curvature metrics. The Euler-Lagrange equation exactly say this vanishes. So
you write the derivative of phi t or
yeah, phi t dot. Yeah, phi t dot is ddt of phi t at t. So at time t. The t denotes too many things. Sorry. For example, the derivative of this path will have phi t dot is just phi, but you can choose another path. Okay, so this one, the critical points are. Okay, let me go there. Constant scalar curvature, Kähler metrics. Unlike the Calabi, which had more critical points in general. But this one has lost the crucial property of positivity. So the critical points of Mabuchi are exactly CSCK. But in general, it's not bounded below. is not bounded below on the space HL. Here let me give you an example. So while the Calabian energy is non-negative, it's always bounded below by 0, this guy might go to minus infinity as you diverge in the space HL. After all, HL is non-compact, so you can definitely diverge. For example, the following. Indeed, if you take V a holomorphic vector field, say not the 0 vector field, not the identically 0 vector field, and then call Ft the flow of, for example, the real part of V. So T is a real parameter, but you can take the complex flow with T a complex parameter, or you can take the complex flow of V if you wish, and nothing changes. So this is a one parameter family of biholomorphisms of X. Then you can pull back a given Kähler metric in the class. This is biholomorphism, and it's connected to the identity because F0 is the identity. So this will still be a Kähler metric in the same class. Simple exercise for you that the class didn't change. It's just the Cartan's formula, just differentiate. And hence, we are allowed to compute the Mabuchi energy along this path. Yep. And well, let's compute instead the derivative of the Mabuchi energy. That's easier. So the derivative of the Mabuchi energy, I just need to drop this, and put here the derivative of these potentials. That comes out to be exactly the Futaki invariant of, what did it denote it? L, omega, of the real part of V in this case. It's an almost trivial check using this, again, this Cartan's magic formula. Again, if you want to get the Futaki invariant of V, you just take the flow of the imaginary part of V. It commutes with this flow, so you complexify time, you get a complex flow. Take the complex derivative, you get the Futaki invariant of V, whole V. So independent of T, this is true for all T. The right-hand side doesn't involve T anymore. So that means the Mabuchi energy is linear along such paths. Mabuchi is linear. And in particular, if this derivative, if this Futaki invariant is not 0, then this will diverge, for example, to plus infinity in one direction, to minus infinity in the other direction. So, and if the Futaki invariant of V, or real part of V, whatever, is not 0, then Mabuchi is unbounded below. I mean, also unbounded above, but as you will see later, it's the below that we care about. So just say it's unbounded below. So this lower bound of the Mabuchi energy appears to be connected to the vanishing of the Futaki invariant. It is. So it appears to be another abstraction to the existence of this constant scalar curvature matrix. Right. So in other words, this proves that if the Mabuchi is bounded below, then the Futaki invariant must vanish in that class. Sorry. L. Okay, so if you want, it's another abstraction, although this is really hard to check if the Mabuchi is bounded below, because you need to check its values on this infinite dimensional space of functions, and it's not so easy. Okay, so to get to the to case stability now, so we have this kind of picture of with infinite many dimensions of the space of Kähler metrics or Kähler potentials, and these energy functionals whose critical points we are seeking to find, and these obstructions given by holomorphic vector fields. So what's the most logical way to say it? 20 minutes, okay. Let me point out the analogy with the finite dimensional case and then discuss case stability. Maybe that's the easier way. So there is an analogy, formal analogy of this picture with the finite dimensional picture of a so-called symplectic quotient or a Kähler quantization. let me just say, of the Kempfness theorem that we saw earlier. Set up. Let me do this briefly since there's not that much time. So in the Kempfness picture, a Kempfness setup that we saw earlier, the finite dimensional setup, we had, again, X, omega, and L as before, and say G, a reductive group, which acts holomorphically on X, and the action should linearize to L as well. So an action, if you want, on the pair XL with, for example, you can just take SLN, SLKC. This would be really the only group relevant for K stability. And then K, real compact subgroup whose Lie algebra complexifies to the Lie algebra of G. So what is it called? Real form? I forgot the terminology. So compact real Lie subgroup with G K plus IK. For example, K SUN, SUK. And then which you assume acts on this, on X omega by isometries. In fact, it's a little bit too much stuff to write. There's also a metric on H, on L, whose curvature is omega, and you want this to act by isometries also of H. Yes. So isometries of omega and H. In fact, for K stability, really the only case that you care about is X is projective space. So you might as well think about projective space here. Then you have a moment map, or let's say the definition of, or maybe let's first say the infinitesimal. You have this infinitesimal action of K. So K acts on X. You can take the derivative. You get a map from the Lie algebra. K is too many things. Sorry. From the Lie algebra of K to the tangent space of X, right? So differentiate the action, d by dt of the action, and let me call a vector here goes into xv. I know x is already the manifold. That's not a very good notation. So then the fact that it acts by isometry means that we have that the Lie derivative of omega is 0, but by Cartan's magic formula, this is simply d of the contraction of omega with xv. So i.e., this is a closed one form, right? So if this actually happens to be exact, then the flow of xv defines a so-called family of Hamiltonian symplectomorphisms. We're not going to care about them now. And a uniform way to put this together for all xv's is the so-called moment map, which is, if you want, a way to find the primitive of these closed one forms, make them all exact in a consistent way with V. So you make them all exact at the same time. So a moment map, if it exists, is a map M from X to, strictly speaking, is the dual of the Lie algebra, but people always identify it with the Lie algebra itself by fixing a by invariant inner product. So pick your choice. And this should be K equivariant, where K clearly acts here. It acts here by coadjoint action. Yes, no. And such that for all V in the Lie algebra, we have, when we take the moment map and you contract it with V, this is the contraction between an element of K and an element of K dual. This is a smooth function on X. I can take the exterior derivative. This is a one form on X. I want this to be the contraction of the Hamiltonian vector field X omega, XV with omega, up to a sign. I'm not quite sure. Is it better to put plus or minus? I'm sorry. It's not a well-established notation, let me put plus, but perhaps you want a minus in this formula for notational consistency. So in our case, the moment map actually always exists by this linearization assumption. So it's not an assumption to assume that it exists in this case, but in general, it doesn't exist for general actions. And the simplest one to keep in mind is this. The action of K is SU n plus 1, G is SL n C, n plus 1 C, X is Pn, L is O1, and then the moment map M from CPn to SU n plus 1. I'm going to drop the dual again. It's the following. You just take a Z0. Here the action is the obvious one, right? The usual action. The action that realizes CPn as a coadjoint orbit. If you want this, you just map it to. Since it's SU, I need to add root minus 1. And then the traceless matrix A, so A minus trace A over n plus 1 identity, where A is the following matrix. A I j bar is Z I Z j bar divided by Z squared, summation of modulus of Z squared. So the numerator or denominators do not make sense on CPN, but the ratio does. It's homogeneous of degree 0. So it makes sense. Each of these is a function, so you get a matrix. And take the traceless part, put I. This is the moment map. Interesting exercise for you. So what do? You again go back to this setup, Kempf-Ness setup. You have this metric H. Let me just call norm the norm of H on vectors on L. In fact, probably you need to take L dual. So of H dual in L dual. L should be O minus 1. L dual should be O minus 1 in the standard picture. So if that's the case, you pick a point, given a point x, pick a lift, a non-zero vector x hat on the fiber of L dual over x, for example, O minus 1. And then look at the following function. Initially goes from G to R. So you have a group element. You want to, this is not the metric, sorry, it's a group element. You take the norm of G dot x hat and take log like this. So the point is that if G lies in K, this norm was invariant by choice, right? I pick metric H invariant under the K action. So if G lies in K, this function is constant. Might as well descend to the quotient, G mod K. Now it's not constant, usually. And this is the norm functional. And it has the property that first it's convex. In the usual, say, Riemannian geometry sense, or since this is a homogeneous space, it just means if you take any one parameter subgroup in this quotient, homogeneous space, then the restriction is convex. That's the cheapest way to say it. And two, if I pick a one parameter subgroup in this G mod K, so this is going to be, take a one parameter subgroup, lambda of T, I'm going to write it as e to the ITV, right? Because V, where V is an element of the Lie algebra of K. So if I didn't put the I, this would be just moving in big K. That doesn't change. So since by assumption the Lie algebra is the complexification, if I move in IK, that's exactly the quotient. So this is the exponential map. So this is the one parameter subgroup I want. And then you can do the log of the norm of lambda T x hat and take the derivative d by dt at t equals to 0. This is actually equal to the moment map at x contracted with v. I'm going to note this as m sub v. again, up to some plus minus 2, some factors that I'm ignoring. Probably it's correct as it is. In particular, critical points of this norm functional are exactly zeros of the moment map. So i.e., the norm functional, its critical points are zeros of M. So zeros of the moment map correspond to critical point of this norm functional. And also, if x is actually fixed by one parameter subgroup, so if x is in the stabilizer, so if x has a non-trivial stabilizer, so if this lambda of t actually fixes x, so you have a non-trivial stabilizer, then this one here gives you an action on the line above x hat. So you have one parameter, a c star action on the line above x hat, and the weight of the c star action on this line, Lx dual, is exactly this MV, plus or minus again. Hopefully it's plus. So this is related to the Hilbert-Mumford weight. So you can recover it from this norm functional. And what's the upshot? The Kempf-Ness theorem, or if you want a simple reformulation in this particular case, says that in this setup, a G orbit contains a zero of the moment map if and only if the G orbit is polystable. Polystable for the action of G, the completely finite dimensional GIT notion from Ian Stock. And if you want, from this, like, if you think about this norm along one parameter subgroups, is convex, and it could look like this. This could be the picture of the norm, with here a critical point, which would be a zero of the moment map. This would be the stable case. This could be the picture, where it's kind of asymptotically going to a constant, but it doesn't quite get to a zero, the derivative. This would be the semi-stable, or say, but not stable case. And then the third case is when it's like this. This would be unstable. So in particular, in this case, you see that the norm functional is proper modulo the stabilizer of this. I mean, here I drew it at a single point. There could be more here. So log norm functional proper on G mod K modulo the stabilizer. G, I don't know, the stabilizer of this orbit, I don't know how to call it. Proper really means in the usual sense. And similarly, for semi-stable, there's a very similar picture. Okay, 5 minutes, great. K stability better come very soon. But it will be essentially the same picture as in infinite many dimensions. And the closure of a G orbit contains a zero of the moment map if and only if the G orbit is semi-stable, if and only if the norm functional is bounded below. And if you want, this is if and only if the infimum over this G orbit. Let's put a norm here, it's zero. This is obvious. I'm just putting because later there will be an analogy. Okay, so the point is that there is an infinite dimensional analog of this picture. I think I really won't have time to tell you the details, but there is a formal infinite dimensional analog of this picture discovered by Fujiki around 2000. No, maybe earlier. I can't remember exactly. And independently rediscovered by Donaldson, who was unaware of it, around 97, I think. where our finite dimensional group K corresponds to the group of Hamiltonian symplectomorphisms of X omega. The Lie algebra of K becomes smooth functions, gets modulo constants. The big group G does not have an analog here. The space X becomes this infinite dimensional space J of complex structures on X compatible with omega. So this is the infinite dimensional manifold where this group of Hamiltonian symplectomorphism acts and where this guy should act. But of course, there is a complexification of the Lie algebra. This is smooth functions, like this. And G mod K becomes exactly the space of Kähler metrics in the class. As I said, I don't have time to tell you the details, but it's quite pretty, the formal picture. This becomes HL, the space of Kähler metrics in this class corresponds to. And lastly, this is formally a Kähler manifold, and the moment map M does become this forming map from J into C infinity of X R mod R. Right, it should go from the manifold to the dual, whatever, of the Lie algebra, and it maps J to the scalar curvature of, well, here I'm emphasizing J. This is the Kähler metric with this complex structure J minus the average. So that kills the constants. So this is really the content. So you can set up this formal picture, and then this requires non-trivial work. That the scalar curvature is a moment map for this problem. So this is Donaldson and Fujiki. And the norm functional, log norm, becomes exactly the Mabuchi energy. And the weight becomes exactly the Futaki invariant. Alpha weight, which is, as we saw, is the derivative of the Mabuchi energy along one parameter subgroups. So with this formal analogy in mind, that is around 97 in there's a volume of field medalist lectures. That's where you can find this, the first place where it appeared. You have the following moral picture. So morally, or a moral conjecture. So this motivated Donaldson to pose that, say here, again, XL as before. Then there exists omega in the first chain class of L, constant scalar curvature Kähler metric. This one should be equivalent to the properness of this norm functional. So Mabuchi energy is proper. On HL. Well, that's not exactly true, right? It's proper modulo the stabilizer. So in a sense, you want it to be proper modulo the automorphism group of this guy. So if you want, you can assume the automorphism group is discrete. Then it's totally correct. No? Omega 0 is a fixed reference metric. Maybe I should put tildes like this. And I'm going to complete this in a sec. So this is a conjecture, right? I will attribute it to everything. Give me a second. And here, similarly, the semi-stable case would be the infimum of over all metrics in this class of the Calabi energy. So the Calabi energy is infimum 0. That is should be equivalent to bounded below. I'm going to drop this in this HL. This would be the picture for the semi-stable case. But then remember, Kempf-Ness also had a stability condition, and that's what you should put here. So this is the conjecture in full circle. So let me say a few things. I said here only really is polystable. If you assume there are no holomorphic vector fields, that's the same as stable. So the conjecture should say polystable. This part here was actually conjectured much earlier by Etienne in 97. And this, so let's see. This arrow here was proved by Etienne around 97. It's okay when L is the anti-canonical bundle, so the Fano case, the Keller-Einstein case. He did prove this part, this kind of analytical Kempf-Ness. Let's see. This part here is the one that I wanted to mention, but I don't have time. Was done in general by Donaldson in 2005 and Stoppa in 2009. Donaldson assumed no holomorphic vector field and got, sorry, take it back. Donaldson didn't assume anything, but he concluded case semi-stable. Stoppa assumed no holomorphic vector fields, and he concluded the K stable. And this is in general, not the minus kx case. And now we know that the whole picture is true. It's true when L is minus kx, thanks to the landmark work of Chen, Donaldson, and Sun. This here. So when L is minus kx, it's totally correct. And in general, it's still open. In fact, in general, I don't think, definitely even this arrow here is open for other polarizations. So not much is known, especially except the arrow above. And this one here also, everything is true. Everything known when L is minus kx. Again, by CDS, Chen, Donaldson, Sun, and also Chili, I guess, pointed out. Basically, Chen, Donaldson, Sun did the hard part of this one. So maybe I should finish very soon. I guess I didn't really define K-stability. It was there. Maybe I can define it. Why not? It was there in your talk, but I should. Otherwise, my title of my talk doesn't really make sense. So just 1 minute or half a minute. The point is that K-stability is the analog of this obstruction with the Futaki invariants that we looked at earlier. So just to remind you, is that, well, really you want to find an analog of the picture of Kempf-Ness, so an analog of GIT. So you want to look, in a sense, find an analog of the Hilbert-Mumford criterion in infinite many dimensions. So you want to look, again, at one-parameter subgroups and compute a weight. The point is, what is the weight? And Donaldson observed two things. First, the one-parameter subgroups can be thought equivalently as test configurations. And second, that the correct weight was a generalization of the Futaki invariant. So this is why the picture comes full circle. So a test configuration for this pair, say x L to the r is any given integer, is the following. It's easy. So normal, I'm going to underline this scheme, x, script x, with a C-star action, and flat C-star equivariant map pi from x to the affine line, where C-star acts on C by multiplication, the standard action, to C-star equivariant L over x, C-star equivariant relatively ample line bundle, such that my original manifold is biholomorphic to the generic fiber of this family. So such that for any t non-zero, this x L to the r is the same as x preimage of t, say. Of course, by C-star equivariance, it's enough to check this at one point. So not for all, but there exists is enough. So just one. And in this case, we're going to say that x is a product. I'm almost done. If x is biholomorphic to a product family, but the C-star action might be non-trivial on the x factor, and then say x is trivial if the same and the C star action is only on the C factor. It's trivial on x. So you're just multiplying here. So the simplest example of a test configuration is a product configuration. But if you assume that x has a C star action, then you can just extend it to the product. So then extend to x. So if you have somebody with a holomorphic vector field which generates a C star action, that's the assumption, then you can construct a non-trivial product test configuration. This is the simplest ones. And in general, I'm almost done. Maybe I should go there. The central fiber is a scheme with a C star action, polarized scheme with a C star action. So x0, L0 is a scheme, polarized scheme with C star action. So you can construct, well, in particular, this gives you a C star action on sections. All global sections. And let's say this one has dimension dk, which is the same as the one of the initial manifold with the L to the R, of course. And then let's say with total weight wk, the total weight of the C star action on this vector space. So then you look at wk divided by k dk. I'm almost done. This one is like some constant plus another constant k inverse plus k to the minus 2, k to the minus 3. This is by Riemann-Roch. And f1 or minus f1 will be the Donaldson-Futaki invariant of the test configuration. The point is that Donaldson computed that in this case of a product with a C star action, the Donaldson-Futaki invariant is equal to the Futaki invariant of the generator of the C star action by equivalent cohomology calculation. So it is a generalization of the Futaki invariant, and end with the case stability is simply that exactly the Hilbert-Manford numerical criterion for all test configurations, which you should think of as one parameter subgroups, and really they are on the Hilbert scheme, then you want this to have a sign. So, and XL is K semi-stable if for all R sufficiently large, and for all X test configuration for X L to the R, we have the Donaldson-Futaki. Sorry, non-negative, non-negative. And K polystable, or maybe say K stable, means for all non-trivial X, Donaldson-Futaki is positive, and K polystable, just like here, means for all X means a semi-stable plus vanishes implies X is a product. Okay, so polystable means the Futaki invariant is a sign, and 0 only when you have a product test configuration, otherwise strictly positive.
What's the difference between stable and polystable?
Strictly positive, and for all, even the product ones. So the only difference is if X has automorphisms. So if X has a C star action, then you have a difference between the two notions. If X has a discrete automorphism, they're the same. So right, if X has a C star action, then one of them is stronger. It says that there can't be holomorphic vector field. So actually, that there is cannot be strictly K stable. Okay, I think I'll leave it to Yuji to continue from here. Hopefully, I got the conventions right, and maybe he will explain why normal here seems to be a crucial technical point, or you're not going to say much about it. Well, we'll see. Okay, that's it. Thanks. Sorry for the overtime.
So since you all want to have coffee, let's save the questions for the coffee break.
Okay.
Valentino.
Thank you. Okay.
Four. The next topic is the 4